Hey everyone, welcome back to another lecture on entropy. Today we're going to talk about standard entropy and entropy calculations. Remember, during the first lecture, we talked about how entropy was defined microscopically if we started looking at the atoms themselves and the way they could be arranged in space and the way that their momentums and energies can be arranged. During the second lecture, we talked about how engineers of steam engines in the 1800s tried to make a better engine, and during that time they studied the flow of heat. They saw that for an engine to run, there had to be something hot and something cold, like coal burning, heating up water in a train, and then the cooler steam being released out into the atmosphere. They realized that some of the energy could be useful as work, but some of it had to just be transferred from hot to cold. And that waste energy, the energy that wasn't useful to do anything, just served to increase the entropy of the universe. Finally, we talked about the impact of transferring heat at a specific temperature. Just like shouting in a library has a big impact, transferring heat to a cold object has a larger impact than when you transfer heat to a already hot object, just like if you started screaming in a high school cafeteria. Our can-do statements, I hope by the end of this lecture you can explain what it means for the entropy to be a certain amount. So maybe like 10 joules per Kelvin for a certain substance at a certain temperature, and describe how that value is determined experimentally. Also, I hope that you can use Hess's law and standard entropy values to calculate changes in entropy during reactions. First, I think it would be helpful to review a few things about different types of energy. First of all, we have the kinetic energy, which is energy of motion, and it's composed of molecules translating, rotating, and vibrating. So A is translating, and here the molecule is just moving in 3 dimensions, like going 2 feet to the left. In B, it's rotating. And when it's only one atom spinning around like a sphere spinning, that doesn't really have too much of an effect. But once a molecule starts having 2 or more atoms, it can start rotating and spinning around and creating all sorts of different angles of rotation. And C is vibration. And in vibrating, the molecules get closer together and farther apart, like 2 things on the end of a spring. The most important thing to know about kinetic energy is that the average kinetic energy is proportional to the temperature. So remember that all of the molecules are going different speeds, but as an average, they make up a temperature. Potential energy, or energy of position, in chemistry has to do with phases and bonds. As heat is added and a substance changes phases from solid to liquid to gas, its molecules become farther apart. Energy is required to counteract the intermolecular forces, which we studied before, the van der Waals forces and ionic forces that are pulling the molecules back together. When the molecules move apart, it's like stretching a spring or a bow and arrow or a slingshot or a person on a swing set propelling high into the air. If we lock into this stretched position, potential energy stored. It can be released when the spring or the arrow or the slingshot is released, and the person swings back to starting position, or the molecules move closer during condensation or freezing. So let's look at this diagram here. Remember, in the solid, the molecules or atoms are very close together. They kind of just vibrate back and forth. They're not really moving too much, and that's why they maintain a rigid shape. In liquids, they're further apart, so the distance between them is a little bit bigger. And it's not big enough that they can just fly all over in 3 directions. That's why a liquid makes a puddle or takes the shape of the bottom of the container. Molecules or atoms can vibrate and rotate and roll over each other, but again, they can't just go in any direction in 3 dimensions. Whereas gas molecules are much further apart. They can do any of the motions that we just looked at: translation, vibration, rotation. And since the molecules are much further apart, they're pulling against the intermolecular forces that are pulling them back together, the van der Waals forces. And so they have a lot more potential energy loaded in gases. Liquids is medium, and solids have much less potential energy because they're much closer together. Just like the person on the swing, when he's not really angled back and just above the ground, he doesn't really have much potential energy in the middle. But as he swings a little bit further, it's like the liquid some potential energy, and then when he's really high up in the air, his potential energy is much greater, and this is just like the gas. Phases is one form of potential energy, and the other potential energy is bonds. When bonds break and different atoms move in or out to form new bonds, the intermolecular forces change, which means a different amount of energy is required to pull them into position. The potential energy stored when they move into position is called the bond energy. Energy is absorbed or released in the reaction when the overall potential energies of position, i.e. the bond energies plus any phase changes, change before and after. So in this picture, imagine the blue molecules right here are two hydrogen, two H2 molecules, and then we have a O2 molecule there in green. And the atoms have a certain amount of potential energy in the molecules. The hydrogen atoms aren't touching, they are a certain distance apart. Same thing with the oxygens. Each of the two oxygens is a certain fixed distance apart in the O2 molecule. They have this amount of potential energy right here to start with. Then, when we rearrange them in the reaction, first we pull them all apart. And just like stretching the slingshot or the person swinging up on the swing, all the atoms are pulling apart and they're fighting those intermolecular forces that are pulling them back together. That's why in the middle, the potential energy is the highest. Then, in this reaction, H2O molecules are more stable than hydrogens and oxygens by themselves. And that's because the intermolecular forces between the hydrogen and the oxygen are different than the intermolecular forces that were just between hydrogen and just between oxygen. And so in these water molecules, there isn't as much energy needed to pull them into the position, into the bonds. So the overall potential energy is much lower after the reaction. And if we actually look at the distance between the potential energy beforehand and after it, that's the energy that's released in this reaction. It's released as enthalpy, delta H. The internal energy of something at a particular phase and temperature is the sum of its kinetic and potential energies. The interesting thing is we can't measure this directly. We can only measure changes. Therefore, there's no absolute internal energy. We arbitrarily define the internal energy to be zero for a pure substance at its usual state at 1 atmosphere and 298 Kelvin. So that's SATP, standard ambient pressure and temperature. Notice that U naught, U with the little circle, is the way that we define internal energy. And so delta U is change in internal energy. When we studied gases, we talked a lot about the cylinder and how useful it is to do gas experiments in. We used a syringe in the lab to approximate this type of cylinder. If you remember that the piston is the way of changing the pressure, so if you lift up the piston, it will decrease the pressure inside the cylinder, or if you push down on the piston, it will increase the pressure inside the cylinder. Additionally, if the gas expands on its own and pressure is increased, the piston will lift up, or if the gas contracts, the piston will be lowered. Remember that when the piston is raised or lowered, work is usually done, and that's because there is some pressure ordinarily from the atmosphere pushing down on the piston. Anytime that we move an object, when there's a force against it, we are doing work, and work takes energy. The classical formula for work is W equals F delta X, where here it's the force that you're moving against times the distance that you, say, push the object on a table or something. With a cylinder, we're actually looking for changes in volume, not just, say, pushing an object in a straight line. If we look at our formula for change in volume, we can say that it's the area of the piston, the whole top of the piston, times this change in height here. The change in volume equals the area times the change in height. And if we plug that formula into the formula for pressure, where we find that pressure here equals force divided by area, and rearrange it so it says F equals pressure times area, then we can find the work, W, equals the pressure times area times the change in height. And we put that negative sign in front of the P to show that the system is doing work when it expands, and EXT means external force. So how hard the plunger is pushing, either from some extra force on it or just from the atmosphere. So again, the final formula is work equals negative pressure surroundings times delta volume. Now, you don't really need to worry about this formula. We're not going to be doing so much calculations right here, but I want to point out that work involves a change in energy. Again, if we look at the bottom here in the purple, work is pressure times change in volume. And if we think about our ideal gas law, PV equals nRT, and this is a gas law about energy, we can say that if we do work, we change the energy. The other way to change energy is through heat. And when heat is flowing, there's usually a change in temperature. If we look at the other side of the ideal gas law, we change energy on the other side, usually by changing the temperature and causing heat flow. We can say, if we look on the right, that the change in internal energy of a system, delta U of the system, is equal to the heat that enters it, that's why it's a positive Q, minus the work done by the gas as it expands, that's minus W. We could also say that it's Q minus pressure times delta volume. Again, I don't want you to worry so much about this equation like for calculations, but I just want you to get in your head that changes in energy are usually from work or from heat flow. The next part of our review comes with talking about enthalpy. We've talked about this before as well, that we know that when things, aka the system, expand in the lab in an open container, they have to lift the weight of the atmosphere off them. This takes work and reduces the internal energy. And if the system contracts, the atmosphere does work on it and increases its internal energy. Having to calculate how much work the system did moving the atmosphere every time we did a reaction would be impossible. Those gas molecules go everywhere if the container is not closed, and it would be impossible to calculate a change in volume. So we instead use a term called enthalpy, which we abbreviate H, that has this work built in and added to the internal energy change. It's kind of like how in Spain or in other countries, the prices have the tax included, so the shopper doesn't have to calculate how much more she will pay upon reaching the checkouts, like in the US. When I was in Spain, they couldn't believe that the prices on the shelf weren't actually the prices that you end up paying, and they didn't understand why you would want a surprise when you end up at the register. They didn't want to calculate the tax for every item, and chemists wouldn't want to either. So enthalpy is extremely useful. Why this is important for us is that delta H, the change in enthalpy, is equal to heat flow when the pressure is constant, such as an open container in the lab. We're very interested in this chapter about heat and heat flow. And when you see a delta H value, most of the time, as long as the container is open and we're at standard atmospheric temperature and pressure, the delta H value is equal to how much heat would flow in or out from a endothermic or exothermic reaction. Here we can see the mathematical proof for it. Remember, we said that delta H is the change in energy, that's delta U, plus the work, and that's the P delta V, the work needed to lift the atmosphere off of it. Because delta U was the heat in and the work out anyway, if we subtract the P delta V and add the P delta V, then we're left with just Q. So we can say that delta H equals Q. Finally, we have previously done heat calculations to determine how much heat was transferred when something was heated or cooled, and change phases based on its specific heat capacity. We use the formula Q equals mc delta T or enthalpies of fusion or vaporization. And we use Q equals mass times delta H fusion, or Q equals mass times delta H vaporization. This graph was very familiar to you. And remember, at the plateau areas, the temperature does not change. That's why it's flat. That's at the horizontal parts. The kinetic energy remains the same because the temperature doesn't change, and kinetic energy is proportional to the average temperature, but the potential energy increases. Remember, that's energy as positions. So as you are changing phases, say going from a solid to a liquid, the liquid gas molecules are farther apart than the solid molecules. Or when you're vaporizing, the gas molecules are much farther apart than the liquid molecules, and that's why the potential energy increases. In the vertical parts, the temperature does increase, the average kinetic energy increases, and basically the potential energy remains the same, and that's where we use our mc delta T. Remember that the C, the specific heat capacity, is different for the solid, the liquid, and the gas. In this chapter, we're going to use molar heat capacities, so we will call it C instead of lowercase c. The capital C is molar heat capacity, and the small c is specific heat capacity. What this means is that we're talking about a material in general, not, for example, a 1 kilogram iron skillet. These molar heat capacities, or molar heats of fusion, or enthalpies of fusion, or enthalpies of vaporization, basically talk about the heat per mole. We just reviewed a ton of stuff. We started with kinetic energy and talked about that was energy of motion and related to temperature, then potential energy and how that's positioned, and it's changed when we change phases or when we rearrange bonds and reactions. We talked about that when gases expand, they do work, and that internal energy is a combination of kinetic and potential energy. We can only measure changes in internal energy, and those changes in internal energy are usually due from heat flowing in or out, or the system doing work, or work being done on the system. We talked about enthalpy having the work built into it that it takes to lift the atmosphere off of the system when it expands in the laboratory under normal conditions. And we talked about the heating curve, that the sloped areas are when temperature changes, like when a solid, liquid, or gas is heated up, and that's due to the heat capacity times the change in temperature. Remember, we're using molar heat capacities in this chapter instead of specific heat capacities where we multiply them by the mass. Before this time, we will just talk about general amounts per mole. And finally, on the heating curve, the plateau or flat areas were when the potential energy changes during phase changes, when things go from solid to liquid or liquid to gas, when they move much further apart. Finally, on this slide, just a reminder that there's no such thing as absolute internal energy or enthalpy. Here, absolute means like you're starting from zero and that there's a definite amount. We arbitrarily define U naught, that's internal energy, to be zero, and H naught to be zero for each pure element at its usual state at 1 atmosphere and 298 Kelvin, which is SATP, standard atmospheric temperature and pressure. So now that we have reviewed everything, let's move on to the new material. Unlike internal energy and enthalpy, where there is no absolute internal energy or absolute enthalpy, entropy is different. Entropy is a measure of how much energy is spread out into something. Since there is no motion at absolute zero, there's no kinetic energy. In a perfect crystal of a pure substance at absolute zero, the atoms are as close as they possibly can be, so the potential energy is at its minimum. Therefore, a perfect crystal at absolute zero has no energy spread out in it, and the entropy is actually zero. It's not arbitrarily zero as in internal energy and enthalpy. This is the third law of thermodynamics. Again, for a perfectly ordered solid, the entropy is zero at 0 K. The third law allows us to define absolute entropy. The absolute entropy of a substance at a given temperature is the sum of all the entropy it would acquire upon warming from absolute zero to that particular temperature, the temperature it's at. Why is this important? Well, because it allows us to calculate entropy changes, which is what we want to figure out when we heat things or during reactions. So how do we calculate absolute entropy or energy changes? Let's start with heat transfer, since we know that in the last lesson that delta S equals Q over T. So if we can find Q, heat transfer, maybe we can find something about entropy change. For example, how much heat would be absorbed by a piece of ice with heat capacity 36.2 joules per mole Kelvin to bring it from 260 Kelvin to 270 Kelvin? We've done these calculations before. So before we use Q equals mc delta T, this time we'll just use Q equals C delta T. Now, if we look at that, we could actually think of Q equals C times delta T as area equals length times width of a rectangle. We could even plot it on a graph, like on the left. The y-axis we could call heat capacity, and that is always 36.2. So that's a horizontal line at 36.2. And then on the x-axis we could plot temperature. So if we go from 260 to 270, those would be the two sides of the rectangle. And since area equals length times width and Q equals C times delta T, the area would be how much heat would be absorbed. So 36.2 times the quantity 270 minus 260 is 362 joules per mole. Let's try the same for entropy. Since delta S equals Q divided by T and Q equals C times delta T, then delta S, if we plug them in and substitute for Q, delta S should be C times delta T divided by T. Or we could just bring out the delta T and say delta S equals C divided by T times delta T. Now, could we just make that the length and the width, where C divided by T is the length and delta T is the width, like we did with heat previously? Unfortunately, the graph of C over T versus T is not a horizontal line, so we can't really find it with area of a rectangle. Maybe we could divide that area up into little rectangles that kind of fit and add up all those areas for an estimation. So this is a spoiler alert where there is calculus magic. Calculus finds the area of infinitely small rectangles and adds them up. Don't worry, we're not going to cover that here, but the final answer in this case is C times the natural log of T final divided by T initial. So if we plug that into our equation, 36.2 times the natural log of 270 divided by 260, we can find that delta S equals 1.37 joules per mole Kelvin. Just like in our heat transfer graph, we also need to add the entropy from phase changes if necessary. No special calculus is needed because the temperature does not change during a phase change. So we can just add the entropy of fusion, delta S fusion, which would be the enthalpy of fusion, delta H fusion divided by T, and or the entropy of vaporization, which equals the enthalpy of vaporization divided by T. The absolute entropy is the entropy added to raise the temperature starting from zero plus accomplish any necessary phase changes to end at the current temperature of the material. So here's an example. What is the entropy of water at room temperature, 298.15 Kelvin? So our strategy would be to start at absolute zero and add all the heat needed to increase the temperature plus the change phases. If you look here on the graph, we are going to go from zero, we're going to go all the way through the solid point, we're going to change phases to liquid, and then go partway through the liquid point. So that would be three different parts of our entropy equation. The first part here, we'll do the heat capacity of ice divided by T times delta T. Then the enthalpy of fusion divided by T as we go from solid to liquid. Then we'll add the heat capacity of water divided by T times delta T. And the delta T for the ice part would be going from 273, which is 0 degrees Celsius, or the melting point of water, and 0K, which would be our starting point. Then we divide our enthalpy of fusion divided by 273K, and then we add our heat capacity of water divided by T times the current temperature, which is 298.15, minus the melting temperature, 273. And if we do all that, we get 70.0 joules per mole Kelvin. Again, we used calculus to kind of make all the little rectangles under the graph and add up the area of the graph. This graph is C divided by T versus T, and it shows how we used area to find the entropy change. This graph is actually entropy S versus T, so not the heat capacity divided by temperature. And this just plots the answer of our calculations, entropy as temperature rises. Notice that entropy jumps at entropy of fusion when things melt, and entropy of vaporization when things turn into a gas. So a key point: the entropy of a substance at a particular temperature T is the amount of energy that must be spread out in that substance for it to exist at that temperature. If it had less energy spread out, the temperature would have to be lower, and or it would be in a different phase. So we just found what is the entropy of water at room temperature to be 70 joules per mole Kelvin. And in our problem, we started from 0 Kelvin and raised it up to room temperature. So the difference here was the entropy at 0 Kelvin on the right and the entropy at 298.15 Kelvin on the left. That difference we call S naught. This is the standard entropy, which is the entropy of a substance at 298.15 Kelvin and 1 atmosphere, and 1 molar if it's a solution. This was SATP. So again, it's the delta S with the initial entropy at absolute zero equaling 0, which was our third law of thermodynamics, and it's the energy that must be spread out in that substance for it to exist at 298 Kelvin and 1 atmosphere. So chemists have fortunately done a lot of the legwork tabulating entropies for us. Here's an example of a table where we have the enthalpy of vaporization, the standard entropy, the molar mass, and the heat capacity. And this allows us to do a lot of calculations. Let's do a quick review. The absolute entropy of a substance at 1 atmosphere of pressure is known as its standard entropy, which was S naught, and it's commonly tabulated for 298 Kelvin. It is found by measuring the reversible heat flow divided by temperature associated with warming the substance from 0 Kelvin, and invoking the third law of thermodynamics, which states that the entropy of a perfectly ordered solid at 0 Kelvin is 0. Thank you, Dr. Stephen Lower, who is the one who made this little flowchart for us. What is a state function, and why do we care? Well, state functions are things that we've been using pretty much the whole time in chemistry, whether or not you've realized it. We've talked about this a little bit before, but the beauty of a state function is that they let us find the change only knowing where we started and where we ended without knowing how we got there. We've seen a whole bunch of problems throughout chemistry where we know the final something, like the final temperature, and we subtract the initial temperature, and that's because temperature is a state function. Enthalpy is another state function. So for example, the amount of energy released, aka the enthalpy change, for the reaction of oxidizing sugar is always negative 2,801 kilojoules per mole, regardless of whether we set it on fire in the lab or whether your body metabolizes it. Other state functions are pressure, volume, temperature, internal energy, that's U, enthalpy, H, and now in this chapter, entropy, S. On the other hand, path functions depend on the methods used. For example, a different amount of work is done if you drive on the freeway directly from downtown to College Park versus if you took the MARTA from downtown to College Park. Examples of path functions are heat, that's Q, and work, W. We studied Hess's law before, but we're going to review it now. Hess's law says we can calculate the amount of heat a reaction will give off or absorb, that is, if it's exothermic or endothermic, without actually performing the reaction, if we can find a series of reactions and reference tables that will add up to that reaction. So let's take the example how much heat is given off when 1 mole of the greenhouse gas methane is burned. Well, first we write our equation. Methane plus oxygen yields carbon dioxide plus water, and we're trying to find the heat of reaction. We look up the heats of formation for each component of the reaction. So we had those tables that looked at the heats of formation. Remember, the heat of formation is how much enthalpy is released or absorbed when 1 mole of something is produced from the bare elements at their usual state at standard atmospheric temperature and pressure. So 1 atmosphere and 298 Kelvin. Well, we look at our reaction. So it starts off with methane. We can find the heat of formation of methane. That is from carbon plus 2 hydrogens, yielding 1 mole of methane. And the heat of formation is negative 75 kilojoules per mole. Then we look at oxygen. Oxygen doesn't have a heat of formation because it is already at its usual state. It's an element. We look at the heat of formation of carbon dioxide. That is carbon plus oxygen, and that heat of formation is negative 394 kilojoules per mole. Finally, water's heat of formation, going from hydrogen and oxygen gas, is negative 286 kilojoules per mole. Now, we have those numbers, and there's 2 ways we can proceed from here. In method 1, we add up the reactions in a way that they cancel out things and then produce the methane combustion reaction. So we had our heat of formation of methane, but in our original reaction, we need methane to be on the reactant side. So we can actually flip the heat of formation reaction. So that is the top line here, methane yielding carbon plus hydrogen. The thing is, then we have to reverse the sign of delta HF. So now we have a positive 75 kilojoules per mole instead of a negative 75 kilojoules per mole. But the carbon dioxide and the water are already on the product side, so we can leave those heats of formation alone as far as their sign. However, our heat of formation was for 1 mole of water, and here we need 2 moles of water in the final reaction. So we're going to multiply that heat of formation by 2. And when we add up these reactions, notice that the carbon graphite cancels and the hydrogen cancel. So that will leave us with the final reaction, methane plus oxygen yields carbon dioxide plus water. And the delta H reaction is negative 891 kilojoules. The other method is a lot more practical because it ends up like that you don't have to start writing out all kinds of reactions and making things cancel. What we really did in the first reaction is we really just added up all the heats of formation of the products and subtracted them from the heats of formation of the reactants. And that's what this equation here in the green box shows. We're adding up the heats of formation of the products and subtracting them from the reactants. Those sigma signs look, I know, scary if you don't really like math or whatnot. And these n's and m's just say, remember to multiply them by the coefficients in the equation. So for example, you produce 2 waters in the above reaction, you need to multiply the heats of formation by 2. So as we follow down in the brown box here, the heat of reaction would be the products first. So we have 1 carbon dioxide, so 1 times the heat of formation of carbon dioxide, 2 waters, 2 times the heat of formation of water, and then we subtract the reactants, 1 heat of formation of methane and 2 of oxygen, and when we add those all up, we get our final number, again, of 891, and that matched our initial result of 891. Basically, this is just a representation of what we did. We are looking to go from reactants to products, so we looked up the heats of formation of the reactants and heats of formation of the products to end up finding the delta H for the reaction. So we already studied Hess's law. Why do we care? Well, Hess's law does not only apply to enthalpy. It actually works with other energy forms as well. This chapter is all about entropy, so you might have guessed that we just reviewed Hess's law because we can use a version of Hess's law to calculate entropy, just like we did for enthalpy. So we have a general reaction, A plus B yields C plus D, and we're going to use our Hess's law, delta S for the reaction equals adding up all the standard entropies of the products and subtracting them from the standard entropies of the reactions, just like we found the delta H to be the sum of the heats of formation of the products and the heats of formation of the reactants. Let's do an example. Let's calculate the standard entropy change when you burn propane in your backyard grill. Well, first step is that we have to write the reaction. So propane is C3H8, and anytime we burn something, we combine it with oxygen. That's a combustion reaction, and it usually forms CO2 and water, and we're trying to find the standard entropy change of the reaction. So first we have to balance the equation. Let's start with our carbons. So 3 carbons on the left, let's put 3 carbons on the right. So next up, let's try to balance our hydrogens. So we have 8 hydrogens on the left. Let's make 8 on the right with 4 H2O. And let's see how many oxygens we have on the right now. We have 3 times 2 is 6 in the carbon dioxide, plus 4 in the water. 6 plus 4 is 10. So if we put 5 oxygen molecules on the left, our equation should be balanced. Now, let's use our Hess's law equation. We are going to try to find delta S for the reaction. And that should be entropies of the products minus the entropies of the reactions. So we have carbon dioxide as a product, and remember we have to multiply it by the coefficient in the equation. Let's take 3 times the standard entropy for carbon dioxide and add that to the standard entropy of water, which is 4 times the standard entropy of water, and we're going to subtract that from the standard entropies of the reactants. So we have 1 times the standard entropy of methane and 5 standard entropies of oxygen. Well, if we look them up in a table, we can find the answer. So I'm just going to plug them all into the equation here. And if we put them all in our calculator, we find that the standard entropy change for the reaction is 100.3 joules per mole Kelvin. Now, let's just go back and think about this reaction. Does the entropy change of the system favor this reaction at standard conditions? Why? Well, yes, because this standard entropy change for the reaction is positive. Remember, when we increase entropy, the reaction is favored. Now, we did all these calculations, but we might have been able to just look at this reaction and thought about it and determined whether or not there would be a positive entropy change, i.e. whether it would be favored. One thing that's important to know is all of these reactants and products are gases. And on the first day, we talked about if we increase the number of energy carriers, we are increasing entropy. And all of the gas molecules are energy carriers. So if our reaction produces more total moles of product than we had moles of reactants, then we are increasing entropy. So if we go back and look at a reaction, we have 6 moles to start with, and we have 7 moles that we end with. So we've gone up in 1 mole. So this reaction is favored entropically, and we knew that just by looking at it. But the positive 100.3 calculation is very important, and you will be expected to do one of these calculations for your exam. We're going to practice a lot of these calculations in class, so don't worry. Well, we are finally done with the third section of your entropy lectures. I know this was a lot today. We had a lot of kind of theoretical stuff at the beginning, adding areas under graphs of heat capacities divided by temperatures and adding them all up and trying to find the standard entropy. The reason we covered all that is, for at least for those of you who are mathematically minded, I wanted to show you that starting from zero, basically as we fill up our gas tank of energy by adding heat, that is how we calculate entropy. And the heat capacity is what we use, and we divide that by temperature. And calculus helps us do it. Those of you who have taken calculus or who are in calculus hopefully appreciated that part. If you're not, don't worry about it. Not a big deal. But what we got to basically is the proof, the reason that we can say that Hess's law can be used to calculate entropy changes for a reaction, which is extremely useful deciding if a reaction can take place. When I took general chemistry, my professors and teachers didn't really explain this very well in depth. They just said entropy is disorder, and you're going to calculate entropy changes by using Hess's law. And it made no sense to me. It was really just plugging in numbers. I didn't really see the relevance of it. It just seemed like random math problems to me. And hopefully, as this is unfolding, you're seeing why things actually happen. And in our next lecture, we're going to talk about one of the most important things in all of chemistry, Gibbs free energy. And that's going to be able to tell us whether reactions will likely take place from a thermodynamics perspective.